let's continue our discussion on dimensionality reduction. This section we want to focus on an algorithm called PCA. PCA stands for Principal Component Analysis. It's one of the most popular dimension reduction algorithm that's out there. So let's look at this chart. It's two-dimensional space. In two-dimensional x1 and x2 space, you have bunch of observations which shows as this blue dots. And then assume that we want to reduce it to one dimension. Do you have multiple choices here? You could for different directions, right? So let's assume that you choose one direction that's C1. If you project, remember we said you could do projection onto the lower dimensional space. So now in two-dimensional space, if you want to project onto this line, what happens is these points go there, some of those two go somewhere there, and this goes there, etc., etc. So what you would come back with would look like this. So you have a bunch of points in the middle and then sparse points on the outside. That's coming from C1. What about we project onto this dotted line here? Now you can imagine that this projection, right? This goes there, this goes there, a bunch of them lines in the middle, this goes back here. So that's what you see actually on the second part of this chart. What about you project on C2? Then all of them collapsed in the middle. That's what you saw on here. The question becomes, which would be the axis that I want to project onto? The method that you need to use is really here, shows that you want to select the axis that preserve the maximum amount of variance, as it will most likely lose less information than the other projections. So the conclusion is already clear from those three alternatives, among others as well, right? The top one, which is the C1, would be the preferred projection direction, simply because we want to preserve more variability of your data. And it's also the same kind of conclusion. If you try to minimize the mean squared distance between the original data set and its projection onto that axis, you would find that the top projection C1 direction is still the preferred way. Okay, this is really high level, right? For PCA, we want to find a direction so that you would be able to project all your observation to those directions. We're talking about two-dimensional to one-dimension space here, but in theory, it could be 100 dimensions to 55 dimensions. Okay, let's look at how you can exactly do that in PCA. So you have to leverage something called singular value decomposition, SVD. SVD comes from linear algebra, and what essentially says, it would be that you have your original data, and then that training set has a matrix, number of observations being the row, and number of columns being the features or variables that you are going to leverage. For that matrix X, you would be able to decompose into three matrices U sigma and V transpose. So X would be equal to U times sigma times V transpose. This is coming from singular value decomposition. We're not actually going to discuss exactly how you would be able to do that and what's the underlying theory, but it's really coming from linear algebra. So if you are interested in, you can search SVD, try to understand why X can be decomposed into three matrices. And it happens that in these three matrices, one of them, V, contains the unit vector that defines all the principal components. It's a vector, and it's normalized so that the determinant of that vector is 1. So we call it unit vector. So this V really look like this in these matrices. It's one column, second column, etc., and then turns out to be n columns. That would be your n components. And turns out to be that it's also ordered based on eigenvalues and eigenvalues of the matrices, and it's ordered based on the value of the eigenvalues, so that C1 is corresponding the largest eigenvalue, and C1 is the first component or direction you should preserve in the principal component analysis. And C2 would be the second component. Okay, so the way that you can do it here is you leveraging this SVD based on centered data to come back with your first component and second component. That's in, you can leverage it in a, that's in a scikit-learn, you could leverage SVD. Okay. Once you figure out which would be the components, assuming that in this example that we discussed earlier, for the 3D dimension that you want to project onto two-dimensional space. Once you know what's the direction that you want to project, you would be able to reduce the dimensionality of the dataset down to the d dimensions by projecting it onto the hyperplane defined by the first d principal components. So in this example, we have three original data is three-dimensional, and we want to project onto two-dimensional space. Then you just need to take the first two components of the original X as also original V, right? As a result, you would be able to figure out those two directions, and then you project onto that hyperplane of that two directions actually defined. It can be expanded to multiple dimensions as well. Original data has 10 dimensions. You figure that you want to project onto the first 4 dimensions, then you would figure out the first 4 principal components, and then leverage those directions of the first 4 components. Then you can just reduce the dimension. That's a key concept. So here is the theory. If you have the WD as the first D columns of V, as we said, first D columns of V would be first D components. You use your original data of X times this WD, which is the first D columns of V, submatrices of that V, right? You use this operation of X times WD, that would be your output of your X, new X, which is the d-dimensional projected data of X. And then you can achieve that by doing this. The W2 from your original V transpose dot and then you transpose to take the first two columns, and then use that W2 to use X-centered data dot W2 to get your project data X2D. How about we implement this in scikit-learn, or how about leverage what's available in scikit-learn to achieve PCA? So what you can do is you import the PCA class, and then you define this number of components being 2 as an example for the data that we just studied. Then you can leverage fit underscore transform to your X to come back with your X2D. So you could use SVD that we just discussed and use that projection and dot function, or if it's even easier, just in PCA to leverage this approach to come back with X2D. It's the same as what we just got with this approach. So essentially, this function really shows you that leveraging PCA versus going back to look at what's under the hood, how you can do those step by step. So one thing that you should be aware that would be, as we mentioned, there is a variance or variability of the original data that we want to preserve in a PCA approach, right? So in that case, we want to introduce this something called explained variance ratio. The ratio indicates a proportion of the data set's variance that lies along each principal component. So here it says, if we use that PCA dot explain variance underscore ratio, and then you find the first component explains 84% of your original variability of the data. And the second dimension explains about 14.6%. If you add them up, it's around 98%. It's not all the variance would be explained 100% by first two components. That makes sense just because originally the data is in three-dimensional space, right? Now you project onto two-dimensional space. You actually lost somewhere around less than 2% of the variability of the data. Using this example, essentially telling you it's okay, it's perfect to reduce that dimension from 3 to 2. It's the same thing for high dimensional space. You want to look at all these numbers to see that what would be the proper way, what would be the proper variance explained for your dimensionality reduction algorithm. So with that being said, we want to leverage what would be the right number of dimensions by leverage the explained variance ratio to figure out what would be the right number of dimensions. So what you can do is you do what I just did, add the first dimension up, which would be 98%. Here it says you do that cum sum of these numbers, and then try to find the value, the first point that actually is larger than 0.895, and then plus 1 would be a dimension. That's one way. Second way would be you as simple as instead of using an integer to define your number of components, you use a ratio 0 to 1. In this case, use 0.95 to define your PCA, and you would be able to directly figure out the proper dimensions. So just pay attention to the difference. If you use an integer, then it's a number of components. If you use a fraction number between 0 and 1, it automatically trying to figure out the first a couple of principal components for you in the PCA algorithm in scikit-learn. So essentially, this would be alternative of what has been done here. This is more like a general case. So x-axis is the number of dimensions, y-axis would be the explained variance, as what we just mentioned, right? As you keep adding the components, then you would be able to increase the explained variance, that cumulative sum. So in this example, you see that initially that explained variance goes up rather quickly as you increase the number of dimensions. And after 150, you see that even if you increase more, it actually doesn't help much to improve your variance explained. With 150 dimensions, you're already being able to explain around maybe 95 or 98% of your original variance, versus the original data have 400 dimensions, explains 100% of your variance. That tells you that it's perfect that you want to reduce your dimension to maybe 150. So this graph is something called explained variance graph, and then you want to identify something called elbow. So that elbow tells you where potentially you can set your cutoff. Assuming that we are going to use 95% as our cutoff, then there's a chance that our conclusion would be 125. Just give you a sense on how you would pick the right number. For this graph, you probably think that, okay, if I want 98%, I just want to reduce the original dimensions to 150. That helps you to make a decision on what would be the proper dimension, or what would be the proper principal components in our V matrix. The original X matrix have 400 columns. Now V matrix still have 400 columns, but I can pick the first 150 to do my calculation. Let's look at how PCA are leveraged in the MNIST example that we discussed. So in the MNIST dataset, if you want to preserve 95% of its variance of the original data, all of these pixels, instead of using 784 features or 784 pixels, you are able to reduce it to 150 features. 150 features would already be able to preserve 95% of the original variance of the data. This tells you that reduction actually only make your data set much smaller. The data set is now less than 20% of its original data size. That tells you how powerful this PCA is for the dimensionality reduction, right? You can do the same thing to decompress from 150 features back to 784. However, just because this back and forth, you have a chance of projection loss. The squared distance between the original data and the reconstructed data, what we call it compressed versus so reconstructed data would be compressed and then decompressed back. This difference is called the reconstruction error. So you would be able to do that. So let's see, you can do the reduced first. And then based on reduced, you do the inverse transform to get your recovered X. And the difference between those two, square difference between those two, would be considered to be reconstruction error. Use this as an example. So what do we lose when you do that compress, do that PCA projection? The original 0, the first one, look more like that. A little bit fuzzy, you still would be able to differentiate it from the rest of the numbers. That's really the purpose, right? So even if you compress the data, we didn't lose much information at all. We're still able to differentiate this digit from the rest of the numbers. It's really just an illustration to help you to know, to understand. By doing that compress, by doing that PCA, by doing that projection, we didn't lose much information at all. So that's gist of PCA. There's some other variabilities or some other variations of PCA. One of them is called randomized PCA. Scikit-learn uses a stochastic algorithm called randomized PCA that quickly finds an approximation of the first D components. So what's the theory behind it? We're not actually going to go through, but here you just be aware that if you use SVD on the score solver equal to randomized, then you're actually leveraging the randomized PCA already. By default, scikit-learn is using that randomized PCA already, unless you really want to use rather than the randomized PCA, you can use the full PCA, which is if you change that randomized to full, then you would be able to achieve that. Majority of the time, I just don't see why you want to do that. You should just leverage the default settings for randomized PCA directly. That's one variation. The second variation is called incremental PCA. So it also stands for IPCA. It allows you to split the training set into mini batches and feed an IPCA algorithm one mini batch at a time. In other words, we could apply that PCA online on the fly. So the way that you do it, you do incremental PCA number of components 154, and then you try to use each batch on your training data set. And then based on that, you would come back with your X under reduced of your data set. So again, just pay attention to the key takeaways here. We discussed PCA. PCA would be the first a couple of principal components in your matrices, which is the V matrix, right? Matrix. And then you project onto those directions. In other words, all those first couple of components of your V. And then you need to figure out how to figure out what would be the proper number of components that you want to pick in your algorithm, which would be figuring out the elbow shape of that dimensionality versus variance explained, figure out what would be the proper dimensions that you want to reduce to. And then two other major variation of PCA. One of them is called randomized PCA. The other one is called incremental PCA. I'll stop here and thank you.